Okay, guys, we have attendance 1101 is the code to go in. Don't forget to do attendance. Okay, let's get it started. Happy Tuesday. Welcome back to probabilistic world and probability class, signal analysis. Okay, guys, don't forget to do attendance 1101, the code. Okay, so let's see what we're going to do today and this week in general. We also have exam coming, second midterm. It's a take-home exam, so have fun. But don't use ChatGPT, please, okay? So it means you can open your slides, but not in your computer. If you have, if you can write it somewhere, but don't use ChatGPT for that. I wanted to put it for the weekend, but I think for weekend is not, I don't know, it's a take-home. Anyway, you can do that. But I'm going to make it Friday to all the rules and regulation for university align with that as well. Still, I didn't design the exam, but it should be similar to the first midterm. But the topics that we had after that till end of the week, okay? So that's about midterm. So what we're going to do today, we already talked about random variables, continuous random variables, and specifically Gaussian random variables. So what we said about Gaussian random variables, what that means? If we say this random variable is Gaussian, or if this set of random variables are Gaussian, what that means? Anything coming to your mind? Anything remember what that means if I say this group of random variables are Gaussian? Yes. Yes. So yeah, but what that means? Yeah. So, but I want deeper. So I want deeper explanation. So we are saying these x's are Gaussian. So what we are explaining when we say is Gaussian, what is relationship between these x's? I already answered. Gaussian. Gaussian relationship. So when I'm saying this set of variables are Gaussian, yes? Yes, exactly, yes. So we are saying relationship between these variables distributed in a Gaussian shape. So it means they are around the mean. So they have more chance to be close to the mean. So that's what we are talking about, when we are saying about not just Gaussian, any family of random variables, we are kind of defining relationship between those variables. That's very interesting. In Gaussian, we talked about Gaussian a lot last class, but we had a delay 1 week, so I'm going to cover a little bit more about Gaussian, more characteristic of Gaussian, and then we're going to go to hybrid random variables. Is it possible to mix discrete random variables with continuous? Yes. In some applications, we have this situation. For example, when you are using, for example, LiDAR or sonar or other sensors that give you distance, you can say, OK, this distance, if it's x, can follow, for example, uniform distribution or random variables. So it means this x, for example, is between 1 meter to 10 meter, but the probability of detection is all equal. For example, is 80%, this LiDAR can detect the distance. So this part is uniform. Uniform is continuous. But sometimes, when we say but, it means we are adding some extra things. But if it's failed, in that case, probability is not following uniform anymore. We are saying, for example, if it failed, it just returns 0. In some specific points, is not following same distribution. So modeling these things can happen using hybrid random variables that we're going to see today how we can model it. We need to see what is delta function or Dirac function and a step function later. Probably you know them in other courses. Do you know that? Yeah? Have you had signal? Yeah. And you have with this at the same time? This is very related. Yeah, in signal and systems, if you have those, it's a very hard course anyway. So same things. So we're going to cover that as well today, if we get chance. As far as we can finish, probably we're not going to go deeper in hybrid random variables. We can talk about that next class. OK, let's go back and review, a recap about Gaussian random variable. So Gaussian random variable is explained theoretically by central limit theorem. Anybody remember central limit theorem? That was an amazing theorem, actually. You can explain so many things using central limit theorem. Of course, yes.
If you have enough events, eventually will converge to a normal distribution.
Yes, but it's not precise. If you have what? Enough what?
Enough
repeating?
Repeated probabilities, it will become a normal.
OK. Any other explanation is correct, but is still need a little bit more. Any other? Do you remember what was central limit theorem? If you have lots of random variables that you don't know their distribution, you have lots of random variables, x1, x2, you don't know their distribution, but they are a lot. If you add them up, the overall distribution followed this form. It's exactly what you said, but when we add them up, and we don't know their distribution, like the rocks that I mentioned, always remember that. You have rocks with different shapes. It means different distribution. You drop them on top of each other at the end. It's going to make that shape. Not at the beginning, but when it's become a lot. So lots of phenomenon in nature happening like that. We don't know their reason. There is so many reasons. They add them up. and the result's going to be random or a normal distribution. So that's why it's so important to study that. And the formula is very interesting because it's symmetric. The symmetry coming from that x minus mu square. So probability of x and minus x are equal. As you can see, they are symmetric around the mean. And the mu and sigma explain this distribution completely 100%. If you have these two variables, you have everything about it. So that's why it's very well known and important to know. So that's a Gaussian. But we also can compute CDF of Gaussian. So cumulative. If we get integral from minus infinity to x of this formula, the shape going to be like that. As you can see, the shape is like this and is between 0 and 1. This is also very interesting. Later on, if you get AI or anything like a machine learning course, you might see something similar to that. It's called sigmoid function. The sigmoid function is not normal function, but is following similar shape. For in machine learning, they use that for training. And the designing the neural network is very amazing. So a sigmoid function is a little bit, still is exponential, of course. I'm just going to write that to mention that. You might see that. It's called sigmoid. And sigmoid function is 1 over, I think 1, I'm not sure, is plus or minus plus e power x. It might be minus, I'm not sure. This function is minus, yeah. Yeah, it might be minus. Yeah, you're right. So this is sigmoid function. It can use, but as you can, that function is like that also. Is actually approximation of a step function. Sigmoid function is approximation of a step function. We're going to see a step function soon in this class. OK, so this was something that, just remember this. We're going to come back to this end of the class, and we see how we can approximate this. I just need to remember that part. OK, so mu is a mean, and this little sigma is a standard deviation. Sigma square is actually variance. Sigma square is variance, and sigma is a standard deviation that is bigger than 0. OK, I'm going to ask you a question. If the sigma going to 0, what happened to that shape? If sigma, the standard deviation, going to 0, what's going to happen to that shape, bell shape? Any idea? Tighter, yes. It's make it tighter, but it make it longer too. Because why did it make it makes it longer too? Why? What? Exactly, because the area need to stay the same. The area need to be always 1. So when this sigma going to 0, it get tighter and tighter, but it get long. Remember that as well. What's going to happen to this shape? This shape going to become close and close to the step function, isn't it? That's interesting. We're going to see that. So this Gaussian distribution is amazing because of this characteristic, these amazing things. Anything else we can say about that? Of course, expected value and variance is this, and it's symmetric around the mean, and the total area is a 1 and is a bell shape. Okay, so we had that last class. Something also very interesting happening in Gaussian, and that's the linear transformation. Okay, what that means. Linear transformation means you have another variable that this variable is a function of x. What about if we transfer variable x by a function g, that this g is a linear? When we are saying linear, it means a relationship between x and y is linear. Like we have some a and b, so y is equal to ax plus b. That's a linear transformation. Like in a space, if you look at the two-dimensional space, it means you are moving one point to another point linearly, like a move it in x and y, something like that. That's why we call it transformation. We are transforming one variable to another variable, x to y. But this transformation is with that the g is a linear, is the simplest transformation. We want to see if we do that, what's going to happen to the distribution. We want to see what is distribution of y in this case. We know distribution of x is normal distribution. We said that's normal. This is showing anytime we say one variable follow, when we say that, it means follow normal distribution mu and sigma square. So it means y, this x is follow this normal distribution. And normal distribution just need two coefficients to explain, mu and sigma. Okay, so x is Gaussian. What's happening to y? Let's see that. Let's compute that. But to understand this, we need a little bit more details. Details about what? Let's clean this up. Detail about this transformation. So we have a variable y that is equal to g of x. Okay, I need to ask you another question. I asked last time too. What is random variable? What is random variable? Tell me. Anybody? What is random variable? Is a function that what? Assign. You don't remember? Assign what? Outcome. Yes. It assigns a number to an event. You're assigning a number to an event, you know. That's definition of random variables. So if we transfer it with this transformation, the event is still event. It's not changing. We are just explaining that differently. So transformation is not changing event. Event is the same. Like, for example, event is rain. The probability of rain is the event that's happening. So if we transfer it, just with mathematically, we are explaining it in a different way with using G. So event is not changing. So it means what? Probability is not changing. So it means probability of x, the capital X actually. Probability of capital X between X and in a very small portion like d of X, this probability is equal to probability of Y between a small y and y plus d of X. Because we are just, event is still same event, is not changing. And we just represent events differently. I'm going to write this up because you need to know this part to understand all the point. Event is the same. We just represent it differently. That's the important part. When we are transferring a random variable, we are just explaining that differently. We are not changing the event, so the probability of X and Y in a very small part of changing X and Y is still equal. If they are equal, we can write, do you know we can use PDF to explain this? So this can be explained with PDF of X, D of X, and this can explain with PDF of Y, D of Y. So we can find a relationship between PDF of X and Y. So f of Yx is equal to f of xx. Oh, so this is Y, sorry. Y, d of X, d of Y. This is what I wanted to mention. This is I wanted to prove. When we are transforming a variable using any function, that g doesn't need to be linear, any function, the PDF relationship going to be like that. The reason is that reason that I mentioned, probability is not changing in a small portions, of course. So based on this, so we can compute that. So compute what? Compute this. We have a linear transformation. I want to see what's happening to the PDF. This is PDF. So what's happening to the PDF? We just need to change the variables. We consider x is y minus b over b. We find that with changing the variables. So based on this formula that we proved here, we just need to write this up. F of x, this is new x. And d of x, d of y is 1 over a. Based on when you get derivative from that, you're going to get this. And the rest is just put them there, and just simplification, the result going to be something similar to that. Okay, so what you can see here, this is the new mu, this is the new mu, and this is the new sigma square. So it means the distribution of y still is Gaussian, because this is Gaussian, of course, and mu is changing, mu is transferring, but sigma square become like scaled by a, not by b, just by a. That's very interesting. We're going to use them. So I forgot to mention the outcome of these 2 weeks that we're going to see is estimation. I'm going to teach you, and you're going to learn how you can estimate something. And do you remember when I said about estimation a couple of weeks ago, I think? The time that I explained conditional probability. Conditional probability, when I said, like, for example, P of, let's change the color here to don't mix that, P of x given z, for example, this is conditional probability, and conditional probability is the best estimation ever. Best estimation ever is that. What that means? It means probability of x that we want to find given some information. That means estimation. That means estimate. You want to estimate that. But this is probability. Somebody, maybe you ask me, this is probability, it's not x. How get out x from it? You tell me. How get x out of this? So what is x? We have, for example, we have this probability. We are finding this probability based on x, and z is information. What is x? No, not derivative. But maybe derivative, but we get derivative for what? What is the best x? Yes? No. Why that? Oh, no. Don't mix it with y. That's another thing. I just want to say about, I'm saying the best estimation of x, whatever z is, coming from this conditional probability. I said that's true. But I'm saying another question, how we can take out the x that is unknown from that conditional probability. That is a big formula. What? Yes. We need to max, actually. We need to maximize. We need to find the x that maximize it. Because when the probability is higher, x is better. So we need to maximize this. So the best x that we call it optimal x is the max of this. However, argmax, of course. Argument max. Argmax of this. That's it. So that means estimation. And this is the best estimator ever. But we just need to break this down. And to do that, we need this information. So that's the main goal of these new weeks. That actually, you know what? That's the whole goal of this course. I hope you understand how you can estimate. Estimation is something that you need to learn when you pass this course. You need to know that. Okay, we're going to have lots of examples, of course, but we need to make you ready for do this. We already explained conditional probability, but we're going to go more in that, especially right now we know random normal distribution. We can simplify this formula soon, and later on you can see Kalman filter, for example. Is that? Kalman filter is something that you can learn in this class soon, in probably next week. Okay, so that was about transformation. That's very important. Transformation, this formula, how we can get this from this transformation. The probability is not changing in a small portion because the event is not changing. Event is event. We just represent that differently. Okay, so let's go more. We don't have time. Okay, so normal distribution is amazing. We also can talk about a standard form of normal distribution. A standard form of normal distribution is around 0. Mean is always 0. And a standard deviation is always 1. How we can do that? So in this case, PDF becomes so simple because mu is 0 and sigma is 1. So we can simplify the formula. And how we can do that, we just need to transfer x to x minus mu over sigma. If you That's a green. Those need to get green or not? Oh, but this is green. Okay, let's see. I'm just going to quickly check to see my recording is working. Yes, yes. Okay, good. Everything good. Yeah, but probably we didn't. No problem. No problem. Okay, let's go to Dirac delta function. So Paul Dirac is a British physicist that in that time working in, of course, quantum. It was after, at the same time, like with Einstein, and he was working on quantum mechanics. Is this guy? You can recognize that he is a physicist from his, no, yeah. Yeah, he is a physicist. In that time, when he was working in quantum mechanics, and in that time, they wanted kind of explain some phenomenon that needed a way to represent something that happened in a one point, like a Big Bang in a one little point happened. How we can model that. And mathematics in that time couldn't explain that, because we don't have a function to be just one point. And so he actually introduced this function that we call it delta function. So this delta, or the Dirac delta function, it has this characteristic. It has this is a delta. Remember, this is delta, and this is sigma. Sigma is a little smaller. Don't make that mistake with sigma. Sigma is mostly used for a standard deviation, and that delta, that is lowercase of that delta, is a Greek alphabet, of course, is Dirac or delta function. So anyway, if you get integral from this function that is not really function, it's going to be equal to 1 from minus infinity to infinity. But the main part is here. This physicist invented kind of this function to just can explain infinity sharp impulses, like impulses that are very sharp, like that, in a very short time happening, and it's going to infinity. And this infinity sharp impulse can be explained using this kind of function. Some people, however, mathematicians didn't accept that. They had fight, not physically, of course. They had fight between mathematicians and physicians, because physicians were so happy. They say, OK, we could explain this with the function. But mathematicians said, oh, this is not a function. You need to find a way. Anyway, mathematicians lost the fight. So they said, OK, we need to fix our function definitions. They called that generalized function. They said, OK, this is not a function, but we call it generalized function. Anyway, mathematically speaking, this is not a function. This is generalized function, because this is going to infinity. If it's a function, means f of, for example, so when you say it's a function, f of x is x2, it means if you give x, you're going to get f of x, something like that. But for delta function is not going like that easily, because in 0, it is going to infinity, and it's not give you a normal number. Anyway, this is called delta function. So delta function is just the ideal mathematical model to represent impulse at a single point. That's it. So like a mathematically, just for explaining that impulse in a very short time, we can use this function. Okay, but it has lots of characteristics. Let's see what is that. We can use that to actually get exact values from a continuous function or continuous variable. Imagine you have a very continuous function that is unknown, and it's unknown function, but you want to get value of some points. Like, for example, you want to see what is this value. This is f of, let's call that like another function. I don't know. Like g of x. This is a function. And is unknown function, but you want to see what is g of, let's call that capital X. And this is a small g of x, a small x. What is this value? You want to find that. But you don't know this exactly. You don't have a function. How we can use that? You can use a step function. You can use Dirac delta function to find those stuff. This is one of the kind. This is called like exact value of continuous variable. Like extract that. It's also used for a spike, to model spikes. It's also used for sampling. We can see application of that. But all of these applications coming from the property of, oh, this is the picture. Another picture. This is actually approximation of that using normal distribution that I explained at the beginning of the class. When the sigma going to 0, this is going to infinity. That's the approximation of Dirac delta function. We're going to see that in next slide too. This is the properties. That's the main property. The main property is called sifting or filtering. Also, we call that filtering too. We are filtering or picking out something from that function. So this is sifting or filtering or picking out. This is very important. So imagine g of x is unknown function. And you want to see what is the value of this g of x in point A, for example. You can use Dirac delta to find that. How? You need to get the integral. You need to get the integral of g of x, product of that with this Dirac function, and the result is g of a. So if you see, I think I have a picture here to show that. This is called sifting. We're going to explain that. This is actually later on. Anything coming to your mind when you see this formula? Is there any similarity with anything you had in math? That one? Yes? Yeah, yes. Yeah, signal and system. Anything coming to your mind? Signal and system? If you had that course, I don't know. This is prerequisite for that, or that is prerequisite? That is prerequisite. Really? Don't know. I didn't know that. I was thinking this is prerequisite for that. Anyway, any idea what this look like? What is this formula? What is this integral? Anything you know about convolution? Yes? You had that, yes? This is not similar to convolution? It is, actually. And do you know the convolution is kind of response to the function? So we call it like a impulse, for example, response, if that is impulse, that it is. So we're going to see that also in when we talk about random processes, probably the last part of the class. We're going to talk about random processes, and we're going to go back to this. But anyway, this is very similar to convolution. Convolution, if you remember, f convolve with g of t, for example, was integral minus infinity to infinity, f of tau, g of t minus tau, d of tau. Later on, we can see that this is a response to a function like that. And that looks like impulse response. So it means what? It means you don't need to know about the g of x. You just can find response of that to impulse to find g of a. Like electronically or electrically explaining that. Okay? So we're going to see that later. I just wanted to see what we are dealing with. We are dealing with signals. We're going to see later that this can be frequency domain, and it makes it simple. And it's a very interesting part. Anyway, I just wanted to mention that to just see what is this shifting in Dirac function similar to convolution. Okay, we also call that filtering. Why? Because we are filtering this g of a out of g of x. Okay, we have a picture here. I will show you. Let's clean this up. Oh, yeah, this is the picture. So as you can see, this is the function that we don't know about it, this yellow function. And we have an impulse or Dirac function in x minus a. And if we multiply them together and get integral, the result is g of a. So that's called shifting. That was the first property. The second property is, of course, sigma in any other parts is 0, just in A is infinity, okay? So that's but this is very important part too. If we scale x, sigma kx scale inversely, like reversely. That's very interesting. You scale x by k, but sigma x is scaled by 1 over k. And however, it's just we don't want the sign part to involve in that. That's why we put that. Okay, so how we can prove that? I'm not going to prove completely. I'm just going to mention the proof coming from this formula that delta x from minus infinity to infinity d of x is 1. So if we change variables to, instead of x, we put kx, we can get something like that. Delta kx d of x, we are changing variables. We can call, for example, u. Let's change this color. U, that is kx. And d of u is k d of x. Okay, we're just going to put that here. So the result's going to be infinity to minus infinity sigma, delta, just u 1 over k d of u. This 1 over k coming from this. And yeah, so that's, the rest can be proved because this is 1. And this can result that one. So that's interesting. That's interesting. If you scale x, a delta function gets scaled reversely. What else we can talk about that? Approximation. Approximation, we already explained. We can approximate delta function using normal distribution when sigma going to 0. Here we considered this epsilon instead of sigma, to don't confuse with the delta. But sigma and that epsilon are same. Okay, when epsilon going to 0, when sigma going to 0, when a standard deviation going to 0, as we explained in that picture, the random distribution becomes Dirac function. Okay, because we explained already that, let's just see the picture here. As you can see here, we get this sigma, because sigma is specified how narrow we are and also how tall we are. Why? Because as we explained, this area under the curve always need to be 1. So when we make it smaller, it gets taller. And when we get very close to 0, it's going to go to infinity. So that's exactly the definition of a direct delta function. Okay, so that's the approximation of that. Let's see, any question about this? This is properties. The first one is the important one. Loss of application, we can see that later. It's called shifting. This property is also important. When we scale x, how actually delta function is scaled. And the rest we already explained. That's good approximation. Why is approximation? Because we are not 100%. We are just approximate that with a function. Because normally that is not a function, but we are approximate that with the limit of a function. When this sigma or this epsilon going to 0. Epsilon is exactly a standard deviation, same. I just put this here with different notation, but they are same. So sigma, this is epsilon. Okay, so what else I wanted to mention here? Okay, I forgot. Anyway, oh, okay, for the next slide, I can explain that as well. What about a step function? Okay, to understand hybrid random variables, we also need to know a step function. A step function is well known. It's a step. And this step function is u. We consider u as a step function is 0 when x is less than 0, and is 1 when x is equal to bigger than 0. So it's like that. This is a step function. We want to see how we can model a step function and what is the relationship between a step function and delta function. There is some relationship. So this is like this and going top. That was delta function. And this is u of x. So what is this relationship? Yes?
The delta function is the derivative.
Exactly. Very good. It's exactly derivative. It's exactly derivative. This is also coming from, do you remember the first slide I mentioned? CDF of normal distribution is like this. What is CDF? CDF is the integral of PDF. So exactly here we can say that too. We can say u of c, a step function is integral of delta function. So that's amazing. So let's see these properties. So what is this interpretation? It can model a sudden change, a switch on, for example, or off. And it can use in signals and systems, of course, and probability and signal processing. And the relationship coming from here, as we saw in that picture, derivative of this step function gonna be delta function. And it means the integral is vice versa. So integral of delta function is actually a step function. This is not normal. This is CDF kind of cumulative. Anytime we have minus infinity to x is cumulative. We are measuring like we add them up. So that's why U of C or a step unit step function represent a cumulative jump. Okay? And the sigma represent the impulse concentrated at one point. Okay, so let's have one example, and we are done. Oh, okay, so this is before example. We need to see that as well. Okay, so we want to see what is actually relationship with discrete random variable. Okay, so so whatever we explain math about Dirac delta, about the step function, maybe you ask, oh, what is this relationship with random variables? Because we want to define hybrid random variables. The random variables that part of that is discrete, part of that is continuous random variables. How we can model that? I explain, okay, I'm going to tell you, and here I'm going to tell you what is relationship between discrete and continuous using these tools that we explained. Okay, so the first things coming, okay, we know the PDF, probability mass function, PMF, probability mass function for discrete random variables is like that. It's like a bar chart, for example. So because it's discrete, so for example, probability at point 1 is that, probability at 2 is like 0.5, and probability in 4 is that. If we add them up, it's going to be 1. So that's the characteristic of PMF, probability mass function. And so we know about probability mass function. And we also know that probability mass function, still we can find cumulative distribution of probability mass function. And the shape is like a step function. As you can see, this is 0, for example. When we get 1, we get this much. We add them up, another add, and the rest is finished to 1. That's a cumulative the distribution function. And CDF exists for all random variables. That's why CDF is so important, because it exists for continuous. It also exists for discrete random variables. But for discrete random variables, it's a step shape. For continuous, is a like a curve. It's like a curvy shape, like that. That's a difference between these two. Okay, so we know that. Nothing new so far. But from this, what we can say? We can say this CDF is capital F. Maybe I write that somewhere else. Capital F. This capital F of x is equal to sigma, because we already talked about U, actually a step function. We can say, okay, it's a probability mass function, xi, add them up with U of x minus xi. So this is explanation of that shape. Probability mass function that coming from that, add them up by this u, that is unit a step function, x minus xi, and it's going to make that shape. That's interesting. Let's get derivative from this. If we get derivative, we know the derivative of, let I change the color, derivative of CDF going to be PDF, f of xx sigma. This doesn't have x, it's going out. U has a x, so we know derivative of u is delta. That's it. This is something that we wanted to find. This is relationship between probability mass function and probability density function, probability density function. So relationship between discrete form and continuous form just can explain with this delta function. That's amazing. So it means any phenomenon that has some part discrete, we just can make that continuous as well. We just need to write it like that. OK, I'm just going to go fast in this example. So I already explained this derivative, and it's going to be that. Oh, I just showed the picture also is not that important. So in this is example. Oh, OK. So no, this is not example. I wanted to mention the example, but I need to talk a lot about that. OK, so I'm going to explain this next class, hybrid random variables. Any question? OK, have a great day.